Assalamualaikum. My name is Muhammad Shukri bin Ahmad Adnan. I will be presenting the Gauss theorem and its application in engineering. Simply put, the equation of Gauss theorem is shown in this slide, where Gauss theorem will introduce us an additional method of calculating the surface integral for closed surface S. By this, it means that we have some solid region in space and its boundary will be our surface. Recall that the surface integral for this will be expressed as the surface integral over S of a f dot n ds, where f is some vector field permeating space and n is the normal vector of the surface. Gauss' theorem states that this surface integral is equal to the triple integral over the solid region of the divergence of f dv. Here, dv is our differential value, which in Cartesian xyz coordinates will simply be ds dy dz. If we want to calculate the surface integral of the field over the surface S without using the theorem, we will have to split each of the surface of the shape into their own surface integral and calculate each individually. Luckily, the Gauss theorem reduces our work to one triple integral over the region of the shape. To solve this, we need to recall that the divergence of a vector field is del dot f, where del equal d dx, d dy, d dz. And then this dot product will be solved with triple integral. The Gauss theorem is a useful tool for calculation and it has a variety of application. In fact, the theorem is used in Gauss' law, which application in electrical engineering, to relate the flux of an electric field, which would be the surface integral part of the theorem, to the amount of charge contained within the volume, which would be the triple integral part of the theorem. That's all from me. My friend will show us some examples of this application theorem.
So next, let's look into example number 1. So let S be the surface of the cylindrical solid D whose boundary is x squared plus y squared equal to 4 and z equal to 0 and z equal to 1. Okay, we have got a cylinder here, looks like that. There is z equal to 0 and z equal to 1, and this is the cylinder, x squared plus y squared equal to 4. So that is a circle of radius 2. If you were going to compute this flux integral through the surface, you would actually have to do 1 to 3 surface integral because there is 3 different surfaces. But in this case, we are going to use the divergence theorem, which is a triple integral on the solid D of the divergence of the vector field, which is dv, and that's all we have to do. So to do that, then we are going to need to know what is the divergence of the vector field. So the divergence, which is the vector field f, we take x derivative of x cube, y derivative of y cube, and we take z derivative of z square, and we integrate that on the solid region D with respect to dv. Next, we need to turn that dv into cylindrical coordinates, where z from 0 to 1 are from 0 to 2 because there is a circle of radius 2, and then theta from 0 to 2 pi, and the function we are integrating is 3r squared plus 2z, and then we have r dz dr theta. So to solve the calculation, we are going to use the knowledge we have learned in engineering 1, and we got the answer is 28 pi.
So this cylindrical solid D from the example 1 can be plotted using GeoGebra, which I will show you. So first of all, you need to search 3D graphics in GeoGebra. So all you need to do is key in these three equations based on the example 1, which is this 1, 2, 3. So I have already kicked in this equation and this limit, these two limits. So let me show you. So right here we can see that in between here, this is the cylindrical solid D.
And today I will present about application of cylindrical coordinates divergence theorem. Okay, the question is let D equal to 2x y ax plus x square ay charge per meter square, and find the volume charge density, the flux through the surface on the given limit, and the total charge contained in the region. Okay, this is solution for A. So we can get this the V equal to delta D by D, which is 2x y ax plus x square ay. From this we can derive this equation, division dx over dx plus division dy over dy plus division dz over dz. So substitute the value and we will get 2yc per meter cube. Okay, for B, the flux is equal to the integration surface of d ds, and we can get D is the given equation from the question, 2xy ax plus x square ay, and we substitute D with the equation given. So we can get the definition of S equal to 2x and y, and after deriving it we will get integration of 10 x square dx dz, and after solving it we can get the flux is 1 over 3c. Lastly, total charge in the given area, which is Q enclosed equal to flux. So by this question we can get integration of v dv du, and we substitute into the triple integral of 2y dx dy dz. By solving this we can get the total charge is 1c. Okay, that's all from me. Thank you.
So for the question C, the region where the total charge is contained can also be plotted using GeoGebra within these limits. Let me show you. So you need to key in all these equations which we can find from the question, which is we need to plot in x equals to 2y with this upper and lower limit boundary for x, y and z accordingly, just like this. So let me show you. So as you can see here, the total charge is between here and right here.